Welcome to Oddly Real. I'm Nem Stefanovic. We're all familiar with the concept of time. We keep track of time, we can measure time, and we expect that time will continuously flow forward. But what does it mean to flow forward in time versus moving backward in time? Can we measure the direction of time? More specifically, we can look at the way processes happen in the world, and we also see those moving forward in time too. For example, if I drop some ice in hot water, we all know that the ice cubes will melt and the water will cool down, resulting in warm water. We take this as the forward direction of time, but you don't ever see a warm glass of water spontaneously produce boiling hot water with ice cubes in it. Or think of dropping an egg on the ground. It goes from being a smooth, ovoid shape into a shattered mess. But we don't see smashed eggs spontaneously reconstruct themselves. Why? Would it surprise you if I said the fundamental laws of physics don't inherently prevent processes from reversing themselves in these strange ways? But if not, why don't we see it happening? Interestingly, the answer lies in possibilities. The possibilities of how matter can arrange itself. We're going to talk about what might be one of the more underappreciated concepts in science, entropy. You might not know anything about entropy, or you might have heard that it's a measure of disorderliness or randomness in something. This description doesn't capture the significance of entropy. Entropy is one of the primary movers of the universe. It is a major reason why any actions happen at all. Why do certain chemical reactions take place when you mix substances together, and why do others not? Why is it that two objects in contact with each other, one hot and one cold, result in a warm intermediate state? Entropy is a key reason. The other major player in what moves our universe is, of course, energy. We use energy to do useful work, to push objects around, or to release energy from chemical reactions. But in fact, energy alone can't explain why all of these actions or processes happen. For example, rapidly expanding gases get colder. They aren't driven to release heat energy. Also, evaporating water on skin feels cool as energy is absorbed. Entropy, again, is a significant part of why actions or processes even happen in our world. And as we've alluded to already, entropy is also the measure of the direction of time itself. But we won't be able to fully appreciate entropy until we know exactly what it is. To start, we're going to look way down to the atomic level. Atoms are able to move and rearrange themselves quite readily. They can travel in paths, rotate, vibrate, and they take lots of positions and velocities at any instance of time. Consider a simple example where there are just two atoms moving around in a confined space. Let's track their positions very simply by delineating the left side of the space from the right side of the space. As these atoms move around, they can be either on the left or the right. Since there are only two atoms, we can show all the different possible arrangements. There can be two atoms on the left side or two atoms on the right side within the space. These are actually fairly ordered arrangements since both the atoms are together in one spot. However, the atoms can also be split across the divider where one is on one side and the other is on the other, and vice versa. In this case, they're a little more disordered and spread out. We call these different kinds of arrangements of the atoms microstates. They are micro because they're on the atomic level, and typically we wouldn't see them as human beings. However, the arrangements of these different microstates do impact what we see in our everyday world at the human level, which is what we would call the macro state. Now, this example doesn't actually do us much justice, since there are only a few atoms involved, but you'll see the picture changes very quickly when we add more atoms. For example, let's look at a situation with 4 atoms. We've only added 2 more atoms, but now there are far more possibilities for how the atoms can arrange themselves. Notice now there are still only 2 completely ordered microstates where the atoms are all on the left or right side of the space. But there are far more microstates that are mixed up to varying degrees. There are some microstates where there is still a lot more orderliness with only one atom out of place, but there are more where there is much more disorganization. Now let's take this to a bit more of an extreme, like 2,000 atoms. How many ways are there to organize the atoms so they are completely on the left? Still just one way. But how many ways are there to arrange the atoms so that only one atom is now on the right side of the space? There are now already 2,000 ways to put one particle on the right-hand side. So going from completely well organized as a microstate to slightly disorganized is already a major jump. In terms of possibilities of the different configurations, it's far more probable to be slightly disorganized than perfectly organized. But this just keeps getting crazier. If we look at the number of ways to arrange the atoms where there are 2 on the right, we're up to almost 2 million different microstates. It's far more likely to be in one of these microstates than in the microstates with one atom on the left-hand side. Keep in mind, we're still pretty well organized at this point. It turns out that the microstates with the largest number of possibilities for arrangement are closer to the middle, where the atoms are more evenly distributed between the left and right sides, say about 1,000 on each side. The possibilities for these arrangements of atoms completely dominate in number and likelihood. There are 2 times 10 to the exponent 600 combinations. Just to give you some perspective here, the total number of particles in the entire visible universe is about 10 to the power of 80. And that's just talking about 2,000 particles. If we really want to have some fun, let's look at the number of possible arrangements for the molecules in 18 grams of liquid water at room temperature. That's about what would fill a shot glass. This comes out to this number. Attempting to visualize a quantity of this magnitude is honestly incomprehensible. So clearly, there are lots of ways for particles to arrange themselves, lots of possibilities. The key takeaway here is that when you look at all of the different possibilities of atomic arrangements or different possible microstates, there are only a few well-ordered ones. Most are disordered with a likelihood for the most disorganization. And that's exactly what particles will tend to do, move towards disorganization. It's a statistical inevitability. When you look at the example of the shot glass full of water, the chance that those particles would arrange themselves in one of the few possible ordered microstates is negligible. It's essentially zero. Nature tends towards disorganization. A measurement of these different possible microstates is captured in the quantity that we call entropy. So when there are more possibilities of atomic arrangements, these microstates for any given macrostate, we say there is more entropy. And entropy tends to increase in processes and the whole universe. As a side note, the entropy of a system can be made to be less. We can arrange atoms to be more organized, but this requires an external source of energy. This energy will counteract the tendencies of entropy. Put another way, the entropy of a closed system tends to increase unless countered by the input of energy from an outside source. This is one of the many ways to state the famous second law of thermodynamics. The implications of this are huge, actually universal. If you think of the whole universe as a closed system, meaning there is nothing outside of the universe to add in energy as an input, then the universe will continue to move towards disorder and randomization until it simply can't anymore. There will be no power left, and everything in the universe will be one temperature. We call this end of the universe scenario a heat death. But how does all of this relate to the directional flow of time? We all perceive time to flow forward. We can see this in how the world around us works. You smash an egg, it always falls to pieces, but we never see it reassembling itself. We light paper on fire to see it burn to ash, but we don't see the ashes reconstruct themselves into paper. There's a directionality to these processes, our idea of forward in time. Interestingly, the fundamental laws of physics don't have any mechanism built into them to indicate a direction of time. There's nothing at all in the laws of physics that would prevent an egg from reassembling itself if we were to run the time in that process in reverse. In fact, even more generalized laws, like the law of conservation of energy, are also not violated when these processes run in reverse. Yet, we don't ever seem to see the processes happen in reverse. Why? It comes back to entropy. The chance for the system to rearrange itself spontaneously back into its well-ordered low-entropy form is improbable. Negligible, really, essentially zero. Entropy is really our only measure of time's directional flow, and it explains the unidirectionality of all of these processes. This can also help us to answer a question like, could we encounter someone who is traveling backwards in time while we are moving forward in time? Well, imagine a simpler example in which we've engineered a situation, like launching a few particles to start aggregating towards each other, all heading in a path toward lower entropy. The problem is that we'd need to have complete control over all of these particles, and moreover, it's a temporary, fleeting effect. When those particles are left on their own, they will ultimately move back to disorder and increasing entropy. In fact, even a slight perturbation to those particles from the outside world will again destroy this experiment and result in increased entropy for that system of particles. So is there any chance that someone with all of their biological processes and associated microstates be made to move against increasing entropy and the second law of thermodynamics? The answer is no. I really hope I've given you some additional appreciation for entropy and its momentous role in the workings of our universe. And I hope I didn't scare you about the heat death scenario of the end of the universe. In any case, thank you for watching, and remember, oddly real, really interesting.